So hi everyone. I'm Kostya from Groby Optimization, and welcome to our tech talk. There's a very special topic today, non-convex optimization, and we just released a brand new version of our product, Groby 9.5, with a lot of improvements on non-convex models. With me today, I have Ed, our resident senior mathematical optimization specialist with more experience than the rest of us together, and of course Richard from the technical account management team, and a very special guest, Jarek from our support team, and an absolute expert on that topic. If you want to participate, yeah, you can send in questions. So there's this Q&A panel at the bottom of your screen. Don't use the chat. Yeah, use the Q&A, and we'll take a look in between and try to integrate as much questions as we can. All right. So without further ado, over to Richard.
Oopsie, thank you, Kostya. Alrighty, so for those of you who are returning visitors to our Tech Talk series, welcome back. For newcomers, good to have you. It's almost tradition at this point that in order, it's early morning here in Europe. Early, it's 9 o'clock. To kick things off a little bit with a few questions to get our brain, a little bit into the mood of talking about non-convex optimization. And so the first question we have for you today is whether you ever have implemented your own branch and bound algorithm. So there should be a poll on your screen right now. Yes, no, or what's branch and bound? Let's see what people say.
Yeah. So it's open.
Guys, what do you think? What's going to be the split? Kostya, you can see how this develops, so maybe not.
Yeah, I'm out. That would be unfair.
I think it's going to be 20% yes.
Jarek, what do you think?
I would go for 30. I'm more optimistic.
I think 5. I think it's. Wow. I believe nowadays. I mean, I think in new OR courses, I think this is no longer. I mean, okay, some people might for their PhDs, but let's see what the results tell us.
Okay, so let me share the results, and sorry, it's early, Richard, but I have to tell you were totally wrong.
Oh,
and Jarek was right. So wow, 34% say they have implemented their own branch and bound algorithm at some point. Wow, I'm impressed. 50%, a little more than 50% say no, and 12% say what's branch and bound. So yeah, we'll explain. Really good.
You're in for a ride. Cool. Okay, I'm happy to be wrong. This is really good. Good job, Jarek. Okay, so then next question, just to gauge a little bit more where we are, is whether you ever have formulated a non-convex model. Again, 3 options: yes, no. What does non-convex mean? And same question for my panelists. Jarek, you go first this time. What do you think?
So I think that this will be like 25% yes. Or even, no, let's go for more. I go for 40%. 40%. I have to stay optimistic.
Ed, what do you think?
I think Jarek's being very pessimistic. The fact that somebody is attending this says to me that they probably have. So I'm going to go 82%.
Okay, I'm gonna play it safe and be in the middle there because I think it's gonna be 68.2. Let's see.
There you go.
Wow. Okay, and everybody knows what non-convex means.
Well, Richard, you realize that you won by going 68.2. If you'd gone 68, we would have tied.
Yes, I redeemed myself. Excellent. Okay, and then final question for this. This is going to be a little bit more technical, so have a look at this. So the question here is, which of these 2 models is harder? So on the left-hand side, you have a linear objective function, a linear set of constraints, which is marked by this polytope here. And then you have this xtx less or equal b. You can visualize this or schematically visualize this as a circle. And on the other hand, you have the exact same thing, just that instead of having less or equal than b prime, you have equals to b prime. So the feasible region in this case is this green space, and here the feasible region is this green space. This is just a line instead of the whole area. And the question is now, which of these two models is harder, A, B, or it depends?
Polls are open. So, Ed, your guess? What do you
Actually,
think?
I deliberately asked not to guess because this is actually more tricky than just guessing.
Ooh.
Ooh. I'm first curious to see what the audience has to say.
Okay, we are at 86%. 80. Okay, I'll stop it here. There you go.
Okay. Interesting. I would not have expected this. So, Jarek, since you're our special guest of honor, you can do the honors.
Yeah, I have to admit,
What do you think?
I really like the results, and I really like the people who like chose it depends, because to be honest, of course I would go for B is harder, but there are special cases where it really depends. So going for B or it depends is the way to go. But I personally would go for it depends, because I've seen a lot of models where it really depends, where you look at and you're like, oh, that will be a hard model. And then you're like, Groby says, we're done in a second. And then you realize it really depends on what happens.
Okay, fair enough. Ed, what do you think?
It certainly is hard to argue with anything that Jarek said. I agree with everything he said, but at the same time, I'm going to go with the crowd and go with B. The point being, from the broad conceptual viewpoint, that the convexity of the feasible region in A is a big advantage. And you can't overlook that despite the special cases that Jarek mentioned. So I'm going with the crowd on this one, but I agree that it's appropriate to say it depends. So that's where I stand on this.
Kostya?
Not much to add. So theoretically harder, that would be B. Practically harder, probably C. It depends.
So one thing we should point out here, for if it wasn't obvious, the A is convex, B is non-convex. So that's kind of the, and that's why I would also go with B, generally speaking. But practically, I mean, non-convex problems have, they're solvable. I mean, you know, so it's a bit tricky, but I would probably pick B. Just to, you know, my academia days are too much resonating with me. It's like non-convex difficult. Okay. All right. So now that we're all warmed up and loose and ready to go, I will share my screen now again, but this time I will share a Jupyter notebook. By the way, before anybody asks, and I know everybody will ask, all of this will be available in a link after the tech talk. So since all of you know non-convex optimization, I suspect that many of you have also sat through tons of, or at least a few of introductions to non-convex optimizations. They all typically follow the same structure, where you presented with a concept of non-convexity, maybe with some drawings, and then you get some theorems, and then you see some algorithms, and then it's all pictures, and it's a little bit webinar-y style. And we didn't want to do this. We thought, when we looked at this topic, we said, what can we do? Since we're in the tech talks, we like to do things a little bit different. What can we do that makes non-convex more approachable and a bit more practical. Like what's on a very practical hands-on level, how do you work with non-convexity? What's the problem? What's the challenges? And how difficult is it really? And so we decided to do something. We decided to go take this practical tour. And what we did, or what Jarek did to be precise, he for this talk here, he coded up his own non-convex branch and bound algorithm. And this is what we're going to look at in detail in the next 20-30 minutes. And we're going to walk through the details of like, what does it take? What are the different ways of approaching non-convexity? And then how does Groby do it? And where, why is Groby so much better than Jarek's implementation? No offense. So without further ado, let's get started. The way we're going to do this is we're going to look at one very particular problem, which is this one right here. We're trying to minimize y. So we have two variables, x and y, and we have this set of quadratic constraints. To visualize this a little bit, this is how it looks like. So this is a plot here. You have the y on the y-axis, x on the x-axis, surprisingly. And then you have these green areas are the constraints. So the white area or gray area is the part that is a feasible region. And the question is now, you're given this, solve it. And then, so you look at it and you're like, okay, well, I look at it and I know somewhere here, 66 and 22.4 or something like this is the answer. But I mean, in reality, if you look at this, the problem you have when you come from an optimization background is that local minimum does not mean global minimum anymore in a non-convex space. So in our case, if we color in all the minima, then suddenly it becomes much more challenging because you're like, which one of these do you pick? You don't only have one minimum, you have 5. And you kind of are, if you do a local search, you can end up in each one of them. And so what most of us will probably have learned in their OR courses, if we took OR courses, is to piecewise linearize, right? And so what does that mean? Piecewise linearization means, well, you look at your constraints, and this is a terrible piecewise linearization, but I think it gets across the point. You take your quadratic constraints, your nonlinear constraints, and just make them linear. Just add pieces, linear pieces, binary variables plus continuous variables equals to linear model. And then this you can solve, right? And so this is kind of what people said, because they said nonlinear you can't really do. And in Groby you can actually implement this. So here's a bit of Python code. Let me zoom in a little bit for you to have a better look. What we do here is we just define the model. We set the objective that we just said, and then here we just say z equals to x squared. This is what you say with this general constraint, it's called in Groby, and this basically just adds this piecewise linearization. And then we use this x squared, this z in all these constraints here, and then we optimize. And so when we do this, we solve the model fairly quickly, I guess. It's in 1.4 seconds. But we also see this. And this is where I want to pause for a minute and ask Jarek and my other colleagues what this means and why is this a problem with piecewise linearization?
Yeah, so when I first saw this, I was a bit surprised, to be honest, because I remember when I was studying MIPS, my professor told me that, so it was like one of the first lectures, and he said, nonlinear stuff isn't that hard. We can linearize everything and then just solve the MIPS, which, I mean, isn't wrong. But then in the end, you end up with an approximation, right? And an approximation can have violations in the original model. This is somewhat expected if you, of course, think about it. But at the first moment, I was surprised. And I mean, if we take a picture, if we take a look at the picture you have shown, we can actually see why this happens, right? Because the approximation isn't like super good. So we can imagine that if we solve this approximation, there will be some violations.
Yeah, that makes sense. Ed, do you have anything to add?
I have one thing to add. The reason we get this information that Jarek just described is scroll up to the code that implemented this, is that we used the add gen constraint POW function that Groby offers. If we had done the linearization ourselves, which we can do, we would miss out on the violation information, because if we just get the model from Groby formulated by the end user, Groby has no idea that piecewise linear functions were used to approximate this function. So it's going to have no sense that there were these violations. So I want to emphasize that if you have a piecewise linear approximation of a function that Groby will linearize for you, there are advantages to doing that over doing the linearization yourself.
That's fair.
That's all I have.
That's a good point, actually. Kostya?
Yeah, it's not a bug, it's a feature. Yep.
Very well put. Very well put.
Okay.
Actually, one thing I wanted to add here is that you can actually change it. So this is something interesting. Here you see the violations we have. Let's look at them. For example, you see the best objective we find here is 22.909. Right. And so if we now say, well, our approximation is bad because we still get tolerance violations. And this, by the way, a great point that you can actually, you only get this output because you're using general constraints. You can actually increase the number of pieces you use for your linearization, because up here we used two here, for example, 2 pieces. Here we used 4 pieces, and so on. And here we can say, well, as a default, Groby uses, I think it's 1,000 pieces, but let's use like 10,000 pieces. If we do this and we solve this, 2 things happen actually. Let's go back here for a second. Let's solve this. Here we see with the linearization, we go from a model that has 5 rows, 3 columns, and 14 non-zeros to a model that has 8 rows, 1,000 columns, and 3,000 non-zeros. So if we now obviously increase the number of piecewise pieces that approximate the piecewise the quadratic constraint by a factor of 10, drum roll, that should be another question. What do you think happens to the size of the model? I mean, it probably will also increase by a factor of 10. And in fact, if we see this 5, 3, 14, we go to 8, 10,000, and 30,000, right? And so here, though, 2 things happen. First of all, the warning disappears. Second, before we had 22.09, and now we have 22.91. So this was I mean, it depends on how much violations are only ever relevant for as much as you care. If you only want to know the ballpark of 22, then it's good enough. But if you want to know the exact number, then then you might need to increase your tightening, and then you get from a model that has 5, 3, and 14 to 30,000 and 10,000. Okay, so now this is all very sobering. And yes, you can linearize everything, throw linearization at everything, but ultimately it will become a problem. And this is just one very simple model. Now, what else can we do? And this is kind of where we're going to switch gears, and we're going to look into what we call spatial branching. And so the idea is here in spatial branching that you don't linearize the variables, which is what we did before. What you actually linearize is the non-convexities. And so what that means is that we actually use a very well-known friend here, this branch and bound. And what we do, though, we branch on the non-convexities non-convexity via violations rather than on the node relaxation solution. So what does that mean in practice? Since this is a practical tour. So this is what it means in practice. So you have, and again, I'm going to pause here in a second and ask for some comments from your side. So what we have here is we have at the root node, you just relax everything, complete relaxation, spa day. And then you solve the relaxation. But then what you do, rather than branching on a binary variable, which we don't have here, we actually branch in the space. We cut it in the middle, and the left part gets assigned to one node, the right part gets assigned to another node, and you get from 0 to 50 and then 50 to 100. And the relaxation tightens, as you can see. And here the relaxation tightens as you continue to chop up the space up until you find a feasible solution. So just out of curiosity, and Ed, I'm going to start with you this time. How much of existing branch and bound, like say classical vanilla branch and bound, can be reused for this type of spatial branching?
I think, except for the way the relaxation is created, everything corresponds. You're still dividing up, you're still using the same divide and conquer approach. You still are preserving a key quality, a couple of key qualities, which is every child node has an objective that is no better than its parent. And then let's see, there's one more. So every child node has an objective that is no better than its parent. And so all these connections hold. The same things are true with branch and bound. So the way you prune nodes, the way you cut off nodes based on a cutoff value, all that carries over. The only difference really is how you create these child nodes, where instead of branching on integrality violations like we're used to with branch and bound, we branch on these non-convexity violations that Richard is describing in these pictures that we see here.
Yeah. Kostya, anything to add?
Yeah, and it's not just the branching, right? So you can reuse the whole framework. So everything you do at the nodes, all the techniques that you apply. So I mean, it's difficult to put a percentage on this, but I would say you can probably reuse, I don't know, 90-something% of what you have. The only point is that you have a new special case that you that you need to handle.
Yes, although I would say the way you generate cuts has to be generalized too. So it's not that different. You know, there is a notion of disjunction that carries over, but it's a little bit different. So, you know, the formulas you use to derive Gomery cuts for, you know, MIPS doesn't just magically apply here. You know, you need to think a little differently about how you generate your cuts. But overall, that's what Kostya said is true. The basic notions of pre-solve, cut generation, node heuristics, they all apply.
Cool. Jarek, since you're the star of the show.
Yeah, there's nothing to add. Maybe one last thing is, this is one of the reasons why you see Groby stating solving problem is a MIP.
Yep, we're gonna get to that in in the end. But so since we've alluded to it, now let's actually do this. So so these pictures here, they're not prefabricated or anything. Actually, I'm gonna stop sharing again, and I'm gonna start sharing the third component of this today, which is so this is something. This is what Jarek has written for this. Oops, let me go here. This is what Jarek has written for this tech doc. And so this is an actual branch and bound code. Again, this is going to be available. That is for non-convex optimization problems. So this works, and we're going to see it in action in a minute. But before we do, I thought, Jarek, can you give us a little bit of a structural overview of what's happening here? Maybe talk a little bit about the relaxation.
Yes, sure. So the code is a really vanilla branch and bound, meaning that we start off with first initializing all of our structures. So once we need the original model, the relaxation model, the branch and bound tree, where we just put in the root node in the beginning. And we also have written a small logger just to, you know, have a nice output. And the number of iterations is 0 in the beginning. And the main idea of the branch and bound is to just, you know, have a running loop as long as you have at least one node in your branch and bound tree. in the beginning, we have just a root node, meaning that we will get into this loop. And what we do is we just get one of the nodes in whatever manner, and then we solve the node relaxation. And here is the thing: you could reuse the same code for a MIP branch and bound if I would like to, like rewrite a MIP code, and I would just have to replace the solve node relaxation, because here we are looking at spatial branch and bound. For MIPS, we would have to relax the integers. And what happens then? We will have to somehow check whether the relaxation we have solved is optimal. In most cases, it will be. And then we check whether the bound of the relaxation is above some solution which we have right now. At the beginning, we don't have any feasible point. And this is also one thing which is kind of tricky for vanilla branch and bound, is how do we even get one? And for, let's say for MIPS, you can just try the integer, so the relaxation solution of the linear relaxation, and then maybe round the integers. For spatial branch and bound, what we decided to do is just go the easiest way you can think of and just take the solution of the relaxation and check whether this is a feasible solution in the original model. So I don't think that there is really something more simple. And what we do then is we check, is this point feasible, and is it below the MIP, is it better than what we currently have? And if so, then please update the branch and bound, meaning that update our best solution, the incumbent, and then check whether this node is within the MIP gap already. And if not, then construct 2 new nodes, meaning that we would have to rerun the loop again because we constructed 2 nodes, meaning that we effectively increased the size of the branch and bound tree. And then in the end, of course, sorry?
I'm sorry, go ahead, sorry.
Yeah, then in the end, we increase the iterations and have some nice output and plotting.
So one thing I want to add here is that the update with new solve does one other thing, which is also throws away all the nodes.
Yes.
Like it does this check for all the nodes that are in the queue.
Yes.
So basically, this way, if you find the optimal solution, and you create you find a solution and it's better than the other nodes that you have, this throws out a lot of the nodes, right? This is where
yes,
the
exactly.
comes in.
Yes, and exactly. Then on the right, what you can see nicely in the picture is that in the beginning, the best, so what is the solution of the LP relaxation is just some, let's call it a random point in this feasible set of X, and it isn't feasible right now, right? Because it's just some point in the infeasible region. But as we branch, we can see that on the left, we are lucky enough such that the solution of the linear relaxation is actually a feasible point in the original model. So we are lucky enough to find a point which we can use as an incumbent, and that's pretty quickly, but we are just lucky here.
Yeah, cool. Okay, and then one last thing I want to ask you, since you've already touched upon it, this is the solved node relaxation. This is really the only difference in a way, because this is, I mean, if we had to write out pseudocode for branch and bound, this is probably 98% how it looks like, with the exception of this. Ed, sorry, go ahead.
No, go ahead and finish, but I just want to comment after you're done.
So my comment was that just to have one closer look at this node relaxation, because I think this is, if you were to implement it, you're going to convex yourself, or since, to look a little bit under the hood, a little bit, what does it take beyond the branch and bound framework? This is where that happens. Ed, your point.
Yeah, I think that's true, but it sort of depends on your implementation, in the sense that when you check solution feasibility, it's a little different here than in a MIP code, in the sense that you're no longer checking for integrality violations. But if if relaxation model is basically its own class with its own signature methods, then check solution that difference can be encapsulated in the relaxation model. And I think the same is true for the branching decision, which also in a sense is somewhat different, but all those differences, I think if you implement it in a nice object-oriented way, will be nicely encapsulated in the relaxation model.
Yeah, that makes
So
sense.
with that, I lower my hand.
Okay. By the way, any questions from the audience?
We have questions about piecewise linear. Let's do this a little later when we compare the approaches.
Okay. All right, then let's look at the relaxation now, because I think this is where the magic happens. And I would hand again over to Jarek to walk us a little bit through what's happening here, and what's happening here basically.
So that's let's say main bread and butter of spatial branch and bound. How do we construct the relaxations? And luckily, constructing the relaxations of the square term is not that complicated. So what we do is, if we have a square term and we want to underestimate it, we just take some tangents of the square term, which you can see here on the left. This provides us linear underestimators, which we then can use to construct a linear program as a relaxation of the original model. Now, in our case, we are actually working with the flipped square term, meaning the minus x squared, which is non-convex. And for this, the best linear underestimator is just the secant. So just on the right, you can see just this straight line, which, for this particular problem, it's not like the very good approximator, because you see that the error between the underestimator and the actual feasible region is quite large, but it's still the best convex underestimator we can get. And that's where the term or the idea of branching comes in, because when we branch, this underestimator gets better and better, meaning that we decrease the violation between the relaxation and the actual value or the difference between the feasible region and the underestimating function. And then there is the case of x times y, which, yes, thank you, which is the bad guy in quadratic programming, so to say, because this is where things get interesting. You have a two-dimensional function which is non-convex, so it is neither like concave or convex. And luckily, there was this guy, Garth McCormick, which I think in the 80s provided so-called McCormick envelopes or McCormick relaxations. They were actually named after him, which you can see on the right. You can see that the underestimators is given by like two hyperplanes, which connect all of the corners of this 3D cube. And the overestimators is basically the same, but flipped, right? So connecting also all of the corners, but it's over this non-convex surface. And what you can see here is that in both cases, except for the tangents, which were used in the convex case, our relaxations or underestimators or overestimators, they all depend on bounds of our original variables. So meaning that if you want to, for example, construct the McCormick constraint, the McCormick underestimator of a x times y function, you need finite bounds on the variables. And I mean, there are tricks and there are like heuristics and algorithms or ideas where you can work without the bounds, but in general, the underestimators and or overestimators are just not as good in these cases. So from support side here, I would always recommend, please provide finite bounds for all variables occurring in nonlinear terms. this certainly helps the solver in all cases.
Yeah, and I guess also numerics also become much worse when you come to quadratic terms than compared to linear. I mean, if you multiply 10 to the 6 times 10 to the 6, then that's just not great, right?
Yes, so just providing some finite bounds is not good. So maybe again, one call from the support team, please try to add finite bounds which are well scaled for your problem, meaning that they just make sense in your problem and are not too big.
Yeah.
And then there's also the opposite side, where if you go for too small bounds, you run into similar problems, right? So when we start branching, you can imagine that the bounds of the variables get small very quickly, meaning that then you start to multiply with very small values.
Yeah, I have to find this now. Yeah.
Which this should be at the top.
Yeah.
Which isn't a very good idea either. And this is why often in spatial branch and bound, coders introduce something called the diameter of the node, of the current node, meaning that if the bounds of the nonlinear variables get too small, in order to avoid numerical issues, you just say, okay, regarding the nonlinear variables, we are done. We will not branch any further on the nonlinear variables because the numerics just get worse and worse. Because the diameter is so small, and you have to compute the slope in, for example, in the quadratic case, or also in the McCormick cases, that you would rather want to dismiss it rather than work with it.
And this is what we see here, right? May we say,
yes,
compute the diameter if the diameter is less than a self-max diameter, which I believe is set to 10 to the minus 7.
Yes.
Here, then just return false. Ed, I was about to hand over to you. Good timing.
Yeah, just one thing. So we've got this nice geometric representation of the McCormick relaxations, but key to Yarek's point is that the lower and upper bounds are going to show up as matrix coefficients in your node relaxations because of what he just described. And that's the reason why really small or really big bounds can create numerical problems. So this is another this is one extension of spatial branch and bound that we don't have to worry about in regular MIP branch and bound.
Yeah.
In regular, in regular MIP branch and bound, you can actually, quote, do the McCormick relaxation, but the bounds are 0 and 1, so you don't have to worry about, the coefficients are not going to be a problem.
Yeah, that would be nice models, but everything is 0 and 1. Kostya, do you have anything to add?
No, I think it's so. The beauty of this code is that just from my perspective is it's so simple. So what you see is essentially you change the piece of logic for the relaxation, and you essentially add the correct way of changing existing model components, right hand sides, and coefficients. That's really cool.
I agree. Okay, so now is everybody ready to see it in action? I want to hear a nice virtual yes. To do this, we go back to our Jupyter notebook, and down here we're going to execute this now. And so this is just the solve function we just looked at. So we execute this, and this was pretty quick, by the way, I have to say. And you can see here you have the log file. That was the logger that Jarek mentioned in the beginning of walking through the code. That just shows you where this is, and then finally you see here the solution we already talked about, which is 22.91. So indeed it does work. Jarek, what else do you find interesting about this log file?
So what I like is that we are really lucky enough, I think I've already mentioned this, but we are lucky enough to find incumbent pretty quickly, meaning that you see that something happens, and it was faster than I thought it would be. I mean, okay, nowadays the processors are so good that even simple and not the best code can still be executed very well. And also what's interesting that you can see that we actually only wait for the branch and bound to find the best solution for quite a while, because you see that once we find this last feasible point, which is 22.91 whatever, we just finish. We're just done with the optimization. And this is a factor showing that for non-convex problems, so constructing the relaxation is one thing, and it's one problem on its own. But finding feasible solutions is probably an even harder one, if not at least as hard one as constructing the relaxation.
Yeah. Ed, Kostya, anything to add?
No, I think that covers it pretty well. I guess the only thing I'll emphasize is that getting even a half decent solution early can help the optimization. So even though the incumbent goes for a long time without improving, we are improving on the best bound. And that best bound improvement may be coming partially from the cutoff value established by that early incumbent. And this carries over to regular branch and bound as well as spatial branch and bound. That's all I have to add.
Yeah, one thing I'm sorry, go ahead, Kostya.
No, just maybe a good opportunity to feed into questions that we should be able to answer quickly. So this and maybe that should go to Jarek. The natural question is, of course, so this is a continuous model. So how difficult is it now to consider integrality as well?
Yeah, so consider integrality would be like, you could imagine as adding a branch and bound on top of a branch and bound. Maybe you could see it like this, or you could just see the continuous variables and integer variables as kind of branching variables, so to say. And then you would just have to decide, do we want to branch on integer variables first or on continuous variables? And of course, how do you want to construct the relaxation? These are, I think, the two main factors which you would have to consider. But once you have figured this out and even implemented some very simplistic methods, you would be good to go.
Ed, you get your hand raised.
Yeah, I think you can view branch and bound in a really general sense, that you can have any collection of objects that you can branch on in a way that divides the feasible region so that you don't miss anything. They can be discrete objects. They can be these continuous objects like we have here. They could be other things besides integer variables, like these complex objects used in constraint programming. But as long as you adhere to the divide and conquer approach, where every branch ensures that every feasible solution can be found by one of the child nodes you create from a branch, everything else carries over. And I think the example we just discussed of this mixture of integer variables and non-convex quadratic constraints is just one example of that general viewpoint in action.
Good. So let's see. So one of the questions is, so what Jarek mentioned, the bounds, so that we need finite bounds and hopefully good ones. And the question here is, what does Groby do for problems where you don't have them, but maybe you have them by you can derive them from from other constraints, and are there recommendations what to do with the numerics in that case?
So I said I wanted to answer this one. So Groby has a tremendous amount of what's called bound strengthening, which is basically pre-processing methods to do what you asked about, which is derive bounds implied by constraints in the model. And we had that for linear constraints, and we've continued to extend that for quadratic constraints. So that's the main thing. Regarding numeric focus 3, I would not jump to that immediately. I would start with numeric focus 1 if I thought I was going to have trouble with bounds. And then also, I don't think we have this currently, but there is a notion of optimization-based bound strengthening, where you actually do more extensive bound strengthening than what Groby does, but you can implement that pretty easily in the solver API if you need to. So that's how I would answer that question. I don't know if Jarek has maybe something to add to that or not.
Yeah, maybe quickly we need to move on, but yeah, please, Jarek.
It's very short, so Ed said almost everything. I think one small thing which might be useful to add is that you may see the postponed status for nodes, which often occurs when you don't have bounds, or if the bounds are somewhat problematic in the relaxation of the model. And what we do with these nodes, we just postpone them and wait to obtain some other information from other parts of the branch and bound, which may help to either fathom these nodes or to derive any useful information to work with it. That's it.
I have to say, I love how we name stuff. Postpone, yes, we postpone it. It's like, you know, we are not in marketing, that's for sure.
Yeah, but it adds something to the textbook explanation of branch and bound, right? It's not just infeasible, optimal. No. So let's do this a little later.
No, exactly.
Right.
I think, yeah. I think that's the thing also you see here is like implementing a vanilla branch and bound in the textbook style is not that complicated, but then and this is what we're going to get to now in the final 5-10 minutes of the talk, is to see what Groby does. But before we do, we have one last nugget here for you, which is that which is that, so what we actually, when we run this, we actually get something out here. So let's actually happen when we plot this. Look at when we plot this. And what happens here is that this is actually a recording of the solution process. So what we have here is the same plot as before, and here we have like a play button. And the play button, you will see that we have these blue bars, and these blue bars are the value of the relaxation at that particular node that is being solved. And so if we go back to the beginning and we play this, you can see how the relaxation slowly works its work towards there. Let's pause here for a second and zoom in to have a better look. So here you can really see this is our optimal point that we've explored in great detail now, and you can see how the relaxations just get closer and closer. And then you can see we're at 250 and we're already very, very close here. So let's see what happens as it continues. And by the way, these jitters are just from Plotly, from the library used for this. They're just artifacts, basically. And so now if we go back to the beginning, and this is also again an artifact of the plotting. Also, this is an artifact. So if we now zoom in here and go back out, you see this is the only node that is left at the final iteration. It's one node left, which is the feasible, the optimal solution, right? And so as you walk through here, you can see how the bounds slowly creep up as we continue down the search tree. right? Any comments on this from my colleagues before we show the Groby reality of this?
I think we can keep going. I don't have anything to add. I mean, it just shows how gradually you're able to move the dual bound upward because you process all the remaining node relaxations that have objective 0 or have objective, slightly bigger than 0, and gradually it moves up.
Okay. Cool. Then finally, let's get to what Groby does, because for Groby, this is actually pretty simple, as you may have imagined. So you just define your variables, you set your objective, and you define your constraints. And note the difference now. In the piecewise linear, we had z here because that z was equal to x squared. But when you use the actual non-convex solver, you can just define it directly in the constraint, and then you just set non-convex to 2, and you optimize. And then here, we have, as we said already, optimize the model with 0 rows, 2 columns, and 0 non-zeros. Why this is like this is beyond me, actually, now that I think about it. Because
there
of
are no linear rows. That's what
no
we
linear
call them.
rows. Yes, correct, correct. And then however, your pre-solved model doesn't blow up. And so here you solve it, and you get the solution 22.9, as we already mentioned many times. And one thing I want to point out before we continue is that actually we find the optimal solution, we prove the optimal solution by exploring one node. And if we go back to Jarek's model, we needed, with a vanilla branching bound, we needed 500. Right, so this already tells you what's going on here, and this is improved from 9.1. By the way, when we did this material, this was with 9.1 with the old release. This needed 14 nodes, but with the new 9.5 release that I'm running here, this only needs 1 node. Not that this matters much for this model, but it shows you that there's a lot of things to be learned there still. I would like to quickly do the main takeaways here and then open it up for discussion and Q&A and all the rest. And then we can, if that's okay with everybody. So the main takeaways here really are that spatial branching is just branch and bound. So the most important thing. Non-convex optimization is nothing crazy or magical. It's just branch and bound applied to non-convexity. And the key difference, and one of the key differences how you can think about between piecewise linear approximations and spatial branching, is that piecewise linear approximations are fixed when you hand it to the model. As Ed said, you define them, you hand it to Groby, and Groby says, all right, thanks, I'm going to run with this. Whereas with spatial branching, your branching actually improves or changes as you solve. And so that's a fundamental difference. You start with basically 0 branching or with 0 approximation, and then you gradually go down. So this is a different conceptual approach to it. As Jarek showed, implementing your own non-convex solver is quite easy, and almost as easy as coding your own branch and bound. It's work, but it's not very extensive. However, Groby adds a lot of tricks to be much faster than this. And finally, the conclusion, which is that we're now at a point where non-convexity is no longer a deal breaker for solvability, at least. Okay, with these last words out of my mouth, I will hand it over to Kostya to do Q&A, and also to my other colleagues to give their statements.
All right, so lots of participants, so we also probably get lots of questions. So please send them in the Q&A section. The Tech Talk will officially end in a few minutes, but we will stay on for a little longer and answer your questions. I think a good one for now is a question about the new heuristic that we've added to Groby 9.5. And the question is this something that that you have to use manually? You need to know how to enable it, or is it something that works automatically? What is it anyway? I would add, maybe we can spend a minute on explaining what this actually does. Ed, do you want to start?
Yeah, I'll take a crack at this. So what this heuristic is it basically recognizes that you can apply a solver, a barrier solver that computes a local minimum to your non-convex problem, and that will give you a feasible solution. So that's what this involved, and it is on automatically, and we sort of monitor things and assess if it's taking too long. So I've had real good experience with this, but you really don't need to tune it. You know, so far we haven't seen any cases where you need to turn it off. But if you discover that it seems to be taking a lot of time without helping you, you can contact our support staff and they can give you an undocumented parameter to shut it off. But I doubt that will be necessary. So I think hopefully that answers the question.
All right. Anything to add? Okay,
I think the thing to add would be that the point is that you find feasible solutions quickly, not only to help with the branching, but also because sometimes you just want a feasible solution. You may not need to find the optimal solution, just say like, give me something here, which is something that happens more often than one might think.
Okay. Now let's look at the time. So do we allow to influence the branching process in the sense that you can set a branching priority both for integer variables and for non-convex components? Eric?
So this is currently not the case. So we currently focus the branching priorities for integers only. But if I remember correctly, this was something we wanted to discuss with dev team at some point. So, or Ed, do you have new information?
I don't know. I don't think we've added this functionality yet. The only thing I wonder about, but I don't know for sure, would be if you set a negative priority on the integer variable, whether that would prompt us to branch on the non-convex quadratic constraints first. But I'm speculating, and I don't know the answer to that. So I don't know if there's a way to force it to branch on the non-convex quadratic constraints first.
And playing with branching priorities from the, I mean, the only thing that I would add is playing with branching priorities from the outside is always difficult because you essentially define something on the original model. So if you after pre-solve, things may be different, and so using branching priority as a tool to speed up the process is possible, but it's rare. Okay, let's see. So we are at the top of the hour now. So you know that's the material. So you get access, so you can play with it, and of course you can play with the new release. It's out now. There will be a second session of this tech talk tomorrow if you like to attend again, or if you want to recommend this to someone. We will just continue. So you're free to drop. There will also be a recording. We will just move on with more questions.
And
right.
One last comment from my side for those who are dropping. Thank you for attending. Please send us your feedback. One of the main things here is we want to make this as good as possible. So your feedback is really what drives this. Anything you see that can be improved, that you liked, you didn't like, that should have been better, could have been better, please let us know. It was a pleasure to have you.
Yeah, thanks, Richard. All right, so then there's one question that has been around for a while. The complexity of the piecewise linearization. I think for the example that we've shown, it didn't really make a difference. We just added 10,000 and it went smoothly. But of course, that's not the the normal case, and people may wonder what's the price. So why not just do enough piecewise linear piecewise components, and solve it then. So what's the trade-off here? Ed, do you want to start?
Well, there's no magic formula, at least not that I know of, that says, you add this many segments, you get this improvement of accuracy in exchange for a certain amount of degradation in runtime. So I don't have, a closed form answer. My view is just you think about your model, what is an adequate level of accuracy for your approximation. It really depends on the context of the model and the accuracy of the data that's being input. And you then use the minimum number of pieces that it takes to get that level of accuracy. But there's a certain amount of experimentation that is required there. I don't know if anybody else has a more refined answer than that.
Usually my answer, oh, sorry.
Sorry, go ahead, Jörg.
Yeah, so usually my answer would be it depends, as Ed already said. I guess the more piecewise linear terms you add, like the func pieces, the harder it gets usually. But yes, there is always a trade-off.
Let me add one other thing. We're talking about piecewise linear, but it's important to remember that piecewise linear approximations work best when the functions you're approximating are separable. And by separable, what I mean is you're not really allowed to have those cross terms like x times y. There are some tricks you can do to deal with cross terms a little bit, in the sense that x times y can be represented as the difference of some square terms, but that can get messy. Piecewise linear has certain additional limitations that we didn't really go into here, that the McCormick relaxations and spatial branch and bound don't have, in that the latter are really better suited for handling, products of continuous variables as opposed to square terms.
One thing I will add here is that what we showed is the simplest piecewise linearization that we add as a general constraint. We have general constraints for actually, just if we look at the one we showed, we can see that here it says actually this is not a square general constraint. This is POW, so power, and so this is the power of 2. You can add any number here. You could say 3.5. And so we have also general constraints for sinus, for cosinus, for logarithms. So what I really want to say is that piecewise linearizations are, as implemented in Groby, are your best bet at the moment if you have a truly nonlinear problem. By truly nonlinear, I mean like logs, exponentials, this kind of stuff. This is really your best bet at the moment, until there are other options available, maybe in the future. But at the moment, this is, and it covers a very, very large range. I would say like 98% of all possible univariate nonlinear functions.
Maybe one last thing. So I like to call these general constraints an approximation framework, because what it allows you to essentially define the quality you're looking for, and then get the smallest piecewise linear function. So with the least number of pieces. That's something you can do. So in terms of the maximum error that you will see on the whole function, that's something that is already built in. In that sense, we optimize it, but it's not rocket science. And that's one thing. But of course, that doesn't help you in a situation where the error is where you don't want it. And that's that can of course happen, that you are there at when you look at solutions that are interesting. All right, very obvious question. So what's the maximum problem dimension that in our opinion Groby can handle here? I mean, Richard, you said something like, it's not a deal breaker anymore. So how big can it get?
42. Sorry, I had to. I'll give it over to the experts in a second. In my semi-expert opinion, there is no real rule here. I would say the easier the model is structurally, the larger you can scale. So if your numerics are good, and it's the terms are nice, the scaling is good, then you have good bounds. Then you can push it very, very far. Not quite as far as NIP, but you can certainly go in good sizes. If you have bad numerics, we can build a model with, I would say, 100 constraints, 200 constraints, non-convex, that is just going to be awful. Just by putting 10 to the 9, 10 to the -4 everywhere, and then squaring this, it's just going to die. And they have bad numerical trouble. So it's a key point, I think, for me at least, even more so than with MIP. With non-convex optimization, the better you model and the better you treat your data, the better your results will be, because the things are square, and that just makes complexity higher in terms of the problems that it brings with it. So now over to the real experts.
Jarek, do you want to go first or shall I?
Yes, sure, I can go first. So in my PhD, I was working with a model, non-convex model, which had exactly one optimization variable. And the non-convex optimizers or solvers were not able to solve it. So as you will imagine, my answer will be, it depends. And as Richard said, if you have some structure and if the model is behaving well and the numerics are good, you can solve really large non-convex problems. And as soon as you introduce some, I would call it troubles, it can get very hard very quickly. With that to add.
Yeah, I agree with everything that both Jarek and Richard said. I think, first of all, the nature of these nonlinear problems varies from one model to the next. We already looked at how the McCormick relaxation for squared terms is different than the relaxation for products of variables. So already, a model where all your non-convexities involve just squared terms versus all your non-convexities involve products of continuous variables, those are two different beasts. And also, as is the case with regular MIPS, the size of the model is not necessarily the driver of what makes it difficult, as Jarek mentioned with his, one non-convexity case a minute or two ago, that there's other things in play. And in particular, I do think one of the challenges here is, if you're familiar with MIP, you have some idea of the notion of a weak versus a strong formulation. And I think it's a little harder, unless you've really been thinking about it for a long time, to understand what a weak formulation means in the case of these McCormick relaxations of these non-convex constraints. At least for me, sort of coming from this, from more of an LP and MIP background, I find that to be the case, that I have a more difficult time understanding what a weak formulation is. And the first step to tightening a formulation is to understand what makes your current formulation weak. So to me, that's a bit of a challenge. And then lastly, you know, again, regarding problem size, you can always take a gigantic network and add a few side constraints that are either non-convex quadratic, but trivial, or involve integer variables, but are trivial to satisfy. And you can say, hey, I just solved a giant MIP or a giant non-convex QP, but that's pretty much meaningless. So again, the size is not necessarily the primary challenge.
Let me throw a question back at Kostya at this point. We saw when we had the code from Groby that it said params.nonconvex equals 2. Two-part question actually. One, what's the story behind that parameter? And two, why have it? Like, because based on what we just said, like, yeah, non-convex is great and can solve everything, and we're all very happy and excited. Why have this in the first place?
Yeah, so the problem with non-convex models is that sometimes you get them by accident because you multiply variables, and so for a solver it's difficult to second guess if that's really the intention of the users. So it was a design decision to say, well, if people really want to enable these features, then there needs to be a kind of a hurdle, and that was the that was the reasoning to introduce this this parameter. And there are like different. So what we saw earlier is there's the possibility to convexify a model, yeah, sometimes. So it's not all, if the original model has non-convex components, that doesn't mean that it will be like this after pre-solve. So you can, you know, have different levels of how far do you want to go, and setting this non-convex parameter to 2 essentially means go all the way. And if you still have a you know, non-convex quadratic model after pre-solve, then go ahead and apply all these techniques that we just discussed. We may at some point think about removing this hurdle. I think that's on the roadmap, but people don't know if it's a good idea or not. We learn from our users and find out if it turns to be a. I mean, it may sound strange, right? You want to use this new feature, well, then set this parameter to 2, non-convex to 2, yeah. But it's for the time being, it's intentional. We want people to know what they are doing and to enable something they really want.
Do you know why? I actually don't know the answer to why is it equal 2? Why is it not equal true or 1? Or
well, so if so the question is, well, so if it's 0, then essentially we say no, it's non-convex. Sorry, we're not solving this. If you set it to you try pre-solve, and if pre-solve says, oh, okay, we can manage this and find a whatever linear reformulation, then we do it, and go ahead. But if you know, if that doesn't work, then it's exactly these three levels, and 2 means, you know, go ahead. Go all the way.
cool. I still see 2 questions, one of which I would like to take.
Yeah, I thought so.
So there's a question. This is, can Groby handle a large-scale heat exchanger network synthesis problem? And so I actually have a background as a chemical engineer, and so does Jarek, by the way. The short answer is, what's large scale? The long answer is, it depends. Basically, we have an example for a heat exchanger network from Fiedler's book, I believe it is. And that works, solves very, very quickly. The main problem you have actually, so you can model a heat exchanger pretty easily because that's just quadratic terms with the flows and the temperatures. It's the cost function. So in the cost function, you have often the LMTD, so log mean temperature difference. You have like some weird power to the 0.65 as a cost correlation, and so that really becomes sometimes difficult. My comment would be try it out. I think with Groby 9.5, you have a good chance that it will at least produce some solution. And if it doesn't, then reach out to us, so to Groby support, and we'll very much happily take a look at it because we're very much actively looking for applications such as those. I don't know, Jarek, Ed, Kostya, anything to add?
No, I'm not a chemical engineer. I don't even know how you properly build heat exchangers, so I have no clue how you model
But
this.
there's some hot stuff and then there's some cold stuff.
Okay, and the cold stuff gets a little hotter and the hot stuff gets a little
There
colder,
you
yeah?
go.
And
There
so
you
you
go.
have heat exchange. Wow, thank you. Mind blown.
There you go. Now you have a chemical engineering degree. Go on.
Thank you. All right, let's see. I think we have one question left. I need to read this. Did you try to use lower envelopes for group of terms instead of single terms to get tighter lower bounds? I don't know. Does anybody know if that's if I'm not sure if that's a technique that we use internally. I don't know. Does anybody know?
Well, I'm going to speculate here. I'm not sure exactly what's being asked, but there is this situation where you have a collection of terms that have one variable in common. So you can factor out that one variable in these products. And then what's left is now a linear expression. So you add a linear constraint that defines a new variable to be equal to that linear expression. And now you basically are applying a McCormick relaxation or a lower envelope to this one modified single term. So I'm not sure if that's what's being asked. I don't think we support that yet inside Groby, but I think it's on our list. We certainly are aware of that, and we certainly sometimes experiment with that ourselves to see if that helps performance on models. But I don't think it's in the current version. I guess this would be a good time to mention one other thing. We probably should have mentioned it in closing, that we think we're still really sort of in the low-hanging fruit stage of making improvements to our spatial branch and bound solver. And just as the latest Groby version yielded something like a 7x speed up on the harder problems in our test set, we anticipate some continued significant improvements on the speed and the size of the problems we can solve. So Jarek, anything to add?
Yeah, maybe to follow up on this, if the question meant that you could have a look at terms like multiplication plus multiplication plus multiplication of two variables, and in all you will have three, so x1 times x2 plus x2 times x3 plus x3 times x1. If the question is meant for something like this, then some of our cuts will catch the envelope cuts of the relaxation of these terms. I think that's a combination of, we are using RLT cuts plus PSD cuts. This should catch most of the envelopes, or most envelope hyperplanes, but I'm not sure if that's what was meant, because there is like for multiple terms or large terms in non-convex, in the non-convex area, there are a lot of possibilities for this. So.
Cool.
All right, let's see. think we have a last one, and that's an easy one. Can we use, is Groby 9.5 is out? Can it be used in Julia?
Yes.
Yes. I think as long as Julia
Jarek,
have
more
updated.
positivity.
Yeah, I think as long as Julia have updated their GitHub, yes.
Yeah, I think the correct answer is that that's beyond our control. Yeah, so we don't have our own Julia interface because there are good ones out there. And as soon as they support the new release, we can. I know that a few a few products have already adapted to 9.5, and there will be more in the coming days. Especially because we during the beta program, users could test it already, so it shouldn't be too difficult to do it. But as always, especially with open source, it depends a lot of on the initiative and the excitement of the maintainers. And if they were not excited until now, maybe it's a nice gesture to drop them a note and make them aware of the fact that there is a new release. All right, and I think that concludes our tech talk for today. Thank you so much, Jarek, for being with us, for preparing all that stuff. That was certainly quite some work, but people really appreciate it. I already saw, some people had to leave. Lots of thank you. Learned a lot, so that is really helpful. And of course, also thanks again for Richard for driving the presentation, Ed for all your expertise and also the preparation for this work. Wow. So this seems to be an interesting topic. Let's see if we get to talk about something like this again. Yeah, I'll hand it over to you, Richard, for final words if you want. And the only thing I wanted to say is we're going to do this again tomorrow at a different time. So yeah, that's a second opportunity to come and ask questions or send this to friends and if that time works for them. Richard, please.
I wanted to just give out a shout out to Ed, in particular because he's in Pacific time, so over in Incline Village over in the US. So it's very late for him, and I very much appreciate that he makes the time to basically be available for everybody. Because this is also people in Australia watching, and in Japan, India, so on. This is possible because Ed is staying up late. So thank you very much for going the extra mile.
You're welcome, but it's really not an imposition. It's not like I do it every week. And these tech talks are so fun. It's really enjoyable to interact with our user base in sort of a less formal way than we do at conferences or with webinars. So thanks to the remaining audience for attending, and we hope you got a lot out of this.
Yeah, and then two final comments from my side. One is if you have any ideas for future tech talks that you would like us to cover, do send us a note. We're always looking. We have no clear roadmap or anything. We just do what we feel like, in a way. So let us know. And the second thing is have a great day, great morning, afternoon, evening, wherever you are. It was a pleasure to have you, and see you at the next one. Bye-bye.
Everybody.
Bye-bye.
Goodbye.